Hello there, and welcome. Tonight I want to take you somewhere beyond the everyday, beyond the rush and noise of your ordinary world, to a place where time moves differently and distances stretch into meanings we can barely comprehend. I want to invite you on a journey through the cosmos, specifically through the mysteries that exist right in our own cosmic backyard. If you're watching this from somewhere on Earth, I'd love to know where you are. Are you watching from a city bathed in artificial light? Or perhaps from somewhere where you can still see the stars? What time is it where you are right now? Is it late at night when the world around you has grown quiet? Or perhaps it's early morning when the day hasn't quite begun? If you're enjoying this cosmic journey with me, please like and subscribe, because there's so much more of the universe waiting to be explored together, and I'd love to have you with me for all of it. Tonight, we're going to explore a question that might seem simple on the surface, but beneath it lies something profound, something that challenges how we understand the very nature of space and time and light itself. It's a question that might make you skeptical at first, that might make you think, but light travels faster than anything in the universe, so how could it possibly take that long? But what if I told you that within our own galaxy, the very spiral of stars and dust and cosmic wonders that we call home, light takes 100,000 years just to cross from one side to the other? What if that incredible, seemingly impossible delay reveals secrets about the very fabric of our universe? That's the mystery we're going to explore together tonight, and I promise you, it's far more beautiful and fascinating than you might initially imagine. Think about this for a moment. Light is the fastest thing we know. Nothing with mass can travel as fast as light travels. It moves at 300,000 kilometers every single second. Every second. If you were to travel at light speed, you could circle the Earth 7 times before you finish reading this sentence. You could travel from the Earth to the Moon in just over a second. You could reach Mars in minutes. And yet, that incomprehensibly fast beam of light, when it enters our galaxy and tries to traverse the full span of our galactic home, takes 100,000 years to make that journey. 100,000 years. That's longer than all of recorded human civilization. That's longer than the existence of Homo sapiens on Earth. That's longer than 50 times the entire span of human history as we know it. And in that vast expanse of time, light, this ultimate messenger of the universe, slowly travels across our home. So what's happening? What force, what barrier, what cosmic architecture is slowing down the fastest thing in the universe to such an extent? Is it simply the distance, the sheer mathematical reality that 100,000 light-years is an absolutely staggering measurement? Or is there something else, something we've discovered in recent years, something that changes how we understand the very nature of galaxies themselves? Perhaps it's a combination of factors, a cosmic puzzle that has taken humanity centuries to begin to understand. And the beautiful thing, the truly wonderful thing about this mystery, is that as we explore it, we start to understand not just our galaxy, but our universe and our place within it. Right now, as you listen to these words, light from distant stars is traveling toward you. Some of that light began its journey long before you were born. Some of it began its journey before your grandparents were born. Some of it began its journey before any of your ancestors existed. And yet here it is, arriving at your eyes, at your consciousness, carrying information and light and the fundamental message of those distant suns. You're connected to the cosmos by threads of light and gravity and time. You are part of this incomprehensibly vast structure. And tonight, we're going to understand a little bit more about how that connection works, how that light makes its patient way across the darkness. The Milky Way, our galaxy, is truly a structure that defies easy comprehension. Imagine, if you will, a vast spiral disk of stars and planets and cosmic dust, so large that it takes light itself 100,000 years to cross it. Now, imagine billions and billions of stars swirling within that disk, each one potentially harboring its own worlds, its own possibilities. Imagine the sheer scale of that structure. Scientists estimate that our galaxy contains somewhere between 200 billion and 400 billion stars. That's more stars than there are grains of sand on all the beaches and deserts of Earth. That's more stars than there are individual humans who have ever lived. And yet, the Milky Way is just one galaxy among hundreds of billions of other galaxies, each one potentially just as vast and complex as our own. When we think about this scale, we begin to understand why light's journey across the galaxy takes so long. The Milky Way is roughly 100,000 light-years in diameter. That means if you could somehow ride on a beam of light, it would take you a century of human time for every light-year of distance you travelled. 100,000 light-years means 100,000 years of travel time at the speed of light. At first, this seems straightforward, almost obvious. Of course, it takes a long time for light to travel 100,000 light-years. That's just mathematics, that's just how distance works. But here's where the mystery deepens. Here's where we need to pause and think more carefully about what we're really observing. You see, we have to distinguish between what we measure and what we understand. We can measure the distance across our galaxy. We can observe distant stars and galaxies and measure their light, calculating how far away they are based on the light we receive. But measuring distance is different from understanding what that distance truly means. What forces and structures create it? What causes it to be the way it is? The simple answer to why light takes 100,000 years to cross our galaxy is that the galaxy is 100,000 light-years wide, and light travels at a constant speed, so it takes that long. But the deeper answer, the one that has fascinated and puzzled astronomers for decades, it involves understanding what's actually between here and there, what the galaxy is actually made of, and how that affects the journey of light itself. If you're still here with me, listening to these words in the quiet of the night, I want to ask you something. What have you found most interesting so far? What aspect of this cosmic mystery captures your imagination? Is it the sheer scale of the numbers, the incomprehensible vastness of our galaxy? Is it the paradox of light, the fastest thing in the universe, taking so long to make its journey? Or is it the mystery of what we don't yet fully understand? Please, if you're enjoying this journey, leave a comment below and let me know what fascinates you most. And if you love exploring these cosmic mysteries, please like and subscribe, because we're only just beginning to dig into the truly profound questions about our universe. Now let's think about the Milky Way in a more intimate way. We live in this galaxy. Our sun is one of those billions and billions of stars located not at the center of the galaxy, but roughly 2/3 of the way out from the center toward the edge, in a region we call the galactic disk. From our vantage point here in the suburbs of the galaxy, we cannot see the full extent of our home. We cannot step back far enough to see the entire spiral structure all at once. We see fragments. We see the thick band of stars that cross our night sky, which is the edge-on view of our galaxy's disk. We see bright star clusters and nebulae. We see dark clouds where no light seems to reach us. But we don't see the whole picture, not the way an observer from far outside our galaxy might see it. Yet we have learned, through centuries of observation and scientific discovery, what the Milky Way looks like. We have developed increasingly sophisticated telescopes, from Galileo's simple lens to the giant optical telescopes on Earth to the Hubble Space Telescope and beyond. And through these instruments, we have pieced together an understanding of our galactic home. We have sent spacecraft to explore our local region of space. We have mapped the positions of stars and measured their distances using parallax and other techniques. We have observed the light from distant stars and analysed that light to understand what the stars are made of, how hot they are, whether they're moving toward us or away from us. And through all of this, a picture has emerged. A picture of a vast, complex, beautiful structure that is far more intricate than our ancestors could have imagined. The Milky Way appears to be what astronomers call a barred spiral galaxy. It has a central bulge, a dense concentration of stars, and we believe a supermassive black hole at its very core. From this center, great spiral arms extend outward, like a cosmic spiral staircase curling through space. The entire structure rotates, but not like a solid disk. Different parts of the galaxy rotate at different speeds, a phenomenon that puzzled astronomers for much of the 20th century and led to the discovery of dark matter. The disk is accompanied by a much larger, more diffuse halo of stars and possibly dark matter that extends far beyond the visible disk itself. And throughout all of this structure, there is dust and gas, nebulae and star clusters, remnants of supernovae and the birthplaces of new stars yet to form. When we think about light crossing this structure, we need to recognize that the light isn't traveling through a perfect vacuum. It isn't simply covering distance in empty space the way a spaceship might travel. Instead, light is traveling through a medium filled with matter, a galaxy that is as much about what you can't see as what you can. The invisible dust, the clouds of gas, the warped space-time itself. All of these things affect how light moves through the galaxy. They might not slow down light's fundamental speed, because light always travels at its constant speed in a vacuum, but they can scatter it, redirect it, delay its arrival, they can bend its path, they can absorb it and re-emit it. And when you add up all these small effects across the vast distances of the galaxy, across 100,000 light-years of travel through a complex cosmic structure, they create the remarkable phenomenon we're exploring tonight. Consider for a moment what the journey of a single photon of light might be like. Imagine a photon, a particle of light, released from a distant star on the far side of our galaxy. It begins its journey traveling in a straight line at the incredible speed of light, the only speed at which light can travel in a vacuum. But immediately it encounters the cosmic environment. There are dust particles floating in space, tiny grains of material formed from ancient stars that have exploded and scattered their contents across the galaxy. These dust particles don't stop the light, don't prevent it from traveling. But they can scatter it, changing its direction subtly. The light might be deflected by a tiny amount, sent slightly off course. It continues traveling, still at light speed, but now moving in a slightly different direction. As the photon travels deeper into the structure of our galaxy, it might encounter a cloud of hydrogen gas, one of the vast nebulae that serve as stellar nurseries where new stars are born. The light passes through this gas, but some of it is absorbed. The energy of the photon excites an electron in a hydrogen atom, boosting it to a higher energy level. For an infinitesimal moment, the light ceases to exist as light. It becomes energy bound up in an atom. Then, almost instantly, the electron falls back down, releasing that energy as a new photon of light, which continues on its journey. This process happens countless times as light travels through the galaxy. Each interaction is instantaneous, but cumulatively, across 100,000 light-years, these tiny delays can add up. And then, there's the greatest mystery of all, the discovery that's truly revolutionized our understanding of galaxies in the last few decades: the existence of dark matter. This invisible substance, which we cannot see directly, but whose effects we can observe, permeates the galaxy. It extends far beyond the visible disk of stars, creating a massive halo around the Milky Way. Its gravity shapes the structure of the galaxy, affects how stars orbit, and influences the very fabric of space-time itself. The presence of this dark matter, this invisible cosmic architecture, means that the galaxy is far more massive than the visible stars alone would suggest, and that extra mass, that extra gravity, warps space and time in ways that can affect how light travels through it. The more we've learned about the structure of our galaxy, the more we have come to appreciate its complexity. It is not a simple disk of stars spreading outward from a central core. It is an intricate, multi-layered structure with spiral arms that might be density waves, regions where stars are more tightly packed as they rotate. It has streams of stars being pulled in by the galaxy's gravity, the remnants of smaller galaxies that have been captured and absorbed. It has a thick, turbulent interstellar medium filled with gas and dust and magnetic fields. It has regions of intense star formation where new stars are being born by the thousands, and regions of relative quiescence where stars age peacefully. All of this contributes to the journey that light must take across the galaxy. As you sit with this knowledge, as you begin to understand the full complexity of the structure through which light travels, you might start to feel the wonder of it all settling over you. We live in this structure. Our planet, orbiting our sun, is nestled within this vast spiral of stars and dust and mystery. The light that allows us to see the stars, that allows us to observe distant galaxies and understand the universe, is the same light that has been traveling for billions of years from sources unimaginably far away. Some of the starlight that touched your eyes tonight began its journey when dinosaurs walked the Earth. Some of it began its journey before our solar system even existed. And the fact that this light travels across our galaxy taking 100,000 years speaks to the immensity of the structure we call home. If you're still with me, still listening to these words, still being drawn deeper into the mystery of our cosmos, I want you to think about something. What aspect of this vast galactic structure fascinates you most? Is it the sheer scale, the idea that light itself takes 100,000 years to traverse it? Is it the complexity, the fact that our galaxy is far more intricate and beautiful than our ancestors could have imagined? Is it the dark matter, the invisible substance that shapes everything? Or is it the light itself, those ancient photons that carry messages from the distant past? Whatever captures your imagination, whatever draws you into wonder about the cosmos, I want to hear about it. Please leave a comment below and share your thoughts. And if you find yourself returning to these cosmic mysteries again and again, drawn to the wonder of the universe, please like and subscribe, because this journey is far from over. The human perspective on our galaxy has changed so dramatically over the course of just a few centuries. When Galileo first pointed his telescope at the night sky in the early 1700s, he saw stars. Thousands and thousands of stars in the Milky Way, far more than the naked eye could perceive. This was revolutionary. It suggested that the Milky Way was not simply a river of light, as the ancient peoples had imagined, but a vast collection of individual suns. Yet even Galileo could not have imagined the true scope of what he was observing. He could not have known that those thousands of stars were just the tiniest fraction of the hundreds of billions that make up our galaxy. He could not have known that his own sun was just one ordinary star among that incomprehensible multitude. As centuries passed and telescopes became more powerful, as cameras could capture light and spectroscopes could analyze it in detail, we began to build a more accurate picture of our galactic home. We realized that the Milky Way was not the entire universe, as had long been assumed. In the 1920s, Edwin Hubble made observations that proved there were other galaxies beyond our own, other vast island universes floating in the cosmic void. This shifted our perspective dramatically. Suddenly, the Milky Way, which had seemed so incomprehensibly vast, became just one galaxy among billions. We were not at the center of everything. We were not special in any obvious way. We were inhabitants of a relatively ordinary galaxy, located in a relatively ordinary part of the universe. And yet, even as our sense of cosmic perspective grew, even as we came to understand how small and insignificant we might seem in the context of a universe containing hundreds of billions of galaxies each with hundreds of billions of stars, something remarkable happened. We began to understand that our small size did not make us less meaningful. Instead, it made us more meaningful. The fact that we, creatures of atomic matter, could use our minds to understand the cosmos at all, could observe the universe and comprehend its mysteries, seemed miraculous. The fact that light from the most distant reaches of the Milky Way could travel for 100,000 years and eventually reach our eyes, allowing us to see and understand the universe, connected us intimately to the cosmos. We were not separate from the universe, we were part of it. We were made of the same materials as the stars. We were shaped by the same physical laws that shaped galaxies and light and all of existence. This brings us to a profound realization. When we study light and its journey across our galaxy, we are studying something that touches all of us. Every photon of starlight that reaches your eye, every single one, has traveled an incredible journey to get there. Some of them have traveled across the full 100,000 light-year span of our galaxy. Some have traveled even farther, from galaxies beyond our own. And in traveling to you, they carry information. They tell us about the composition of distant stars. They tell us about the birth and death of worlds. They tell us about the fundamental structure of the universe itself. You're connected to the cosmos through these light beams, connected to events and places and times that existed before you, before humanity, before our solar system was even born. As we move forward in our exploration tonight, as we begin to dive deeper into the specific mysteries of why light takes so long to cross our galaxy, hold on to this sense of wonder and connection. Remember that this is not merely an abstract intellectual exercise, not merely a question about numbers and distances and physical laws. This is a question about our home, about the context in which we exist, about the light that has always allowed life on Earth to see and navigate and thrive. The light of our sun, which makes life possible, is the same kind of light that travels across the galaxy. The elements of our bodies, the iron in our blood, the calcium in our bones, were forged in the hearts of distant stars and carried across the galaxy by countless processes over billions of years. We are quite literally made of materials that journeyed through our galaxy. Understanding why that journey takes so long is, in a way, understanding our own origins. The question of light's journey across our galaxy also touches on some of the deepest questions in astronomy and physics. How do we measure distances in space when we cannot simply travel to measure them directly? How do we understand the structure of our galaxy when we cannot step outside of it to observe it? How do we distinguish between what we can see directly and what we can only infer from observations and calculations? These are not easy questions, and the answers have evolved over time as our tools and understanding have improved. Yet in wrestling with these questions, in seeking to understand how light travels through our galaxy, we have developed a much deeper understanding of the universe itself. Scientists working at observatories around the world and in space have dedicated their careers to understanding these mysteries. They have used the Hubble Space Telescope, which can observe light from the most distant stars and galaxies. They have used the Chandra X-ray Observatory, which can detect high-energy radiation from sources that would otherwise be invisible. They have used ground-based radio telescopes that can detect radiation with wavelengths far longer than visible light. They have used infrared telescopes that can see through cosmic dust that blocks visible light. They have built increasingly sophisticated instruments to map the galaxy, to measure stellar distances, to analyze the composition and motion of interstellar gas and dust. And through all of these observations, a picture has emerged, a picture that is far more complex and beautiful than anyone might have initially imagined. The journey we're taking together tonight is a journey that millions of astronomers and physicists have contributed to over centuries. We are standing on the shoulders of giants, using the knowledge and discoveries of all those who came before us. From ancient observers who mapped the stars in the night sky using only their eyes, to Copernicus who recognized that the Earth orbits the Sun, to Newton who discovered gravity, to Einstein who revealed the relationship between space and time, to modern astronomers who use telescopes of unprecedented power to peer into the depths of space and time. All of these contributions have brought us to where we are now, at a place where we can ask meaningful questions about the nature of our galaxy and the journey of light through space. And tonight, we're going to explore some of the answers that modern science has discovered. We're going to think carefully about what we know, what we can observe, what we can measure, and what remains mysterious. We're going to consider the different possible explanations for why light takes 100,000 years to cross our galaxy. We're going to look at the evidence that astronomers have gathered and think about what it tells us. And as we do, we're going to maintain the sense of wonder and contemplation that is so central to the human experience of the cosmos. We're going to remember that even as we gain more knowledge, even as we answer some questions, new and deeper questions emerge, and that perhaps is the greatest beauty of science and of our human curiosity about the universe. The night sky has inspired wonder in human beings since time immemorial. Our ancestors looked up at the stars and saw stories, saw gods, saw connections between the heavens and the earth. They developed agriculture by observing the movements of stars and planets. They navigated across oceans using the stars as guides. They wove myths and legends about the constellations. And while our modern understanding of the stars is far more detailed and accurate than those ancient understandings, the sense of wonder remains. We still look up at the night sky and feel awe at the immensity of what we're observing. We still feel connected to something larger than ourselves. And when we understand more deeply what we're actually looking at, when we understand that the light reaching our eyes has traveled for thousands or millions or even billions of years, that sense of wonder only deepens. The Milky Way has always held a special place in human culture and imagination. Every human being who has ever lived has seen it. At least those who were in the right location at the right time and looked up at a dark night sky. It appears as a river of light flowing across the darkness, a band of countless stars so close together that our eyes cannot resolve them individually, so we see them as a glowing band. The ancient Greeks called it the galaxy, which comes from the word for milk, because they thought it looked like a river of milk spilled across the sky. And in a sense, that ancient description captures something true about what we're observing. It is indeed a river of sorts, a river of light and matter and gravity, flowing through the cosmic void, carrying with it the messages of billions and billions of stars. But the Milky Way we see is only part of the story. Most of our galaxy is invisible to us. The dust that fills it blocks our view of most of the stars in the visible bands of light. We cannot see the far side of our galaxy with visible light, because there is simply too much dust in the way. We cannot see the true structure of the galactic center for the same reason. We can see only a portion of the galaxy, and we have to infer the rest from observations of different kinds of light and from mathematical models. This is one of the great challenges and also one of the great excitements of modern astronomy. We are trying to understand a vast structure from within it, using increasingly sophisticated techniques to pierce through the obscuring dust and see what lies beyond. The dust itself is part of the reason light takes so long to cross our galaxy. This dust is not like the dust you might sweep off a shelf in your home. It is not simply inert matter sitting passively in space. Cosmic dust is composed of tiny grains, often with compositions that include silicates and carbon, sometimes with ices of water and other molecules. These grains are small, typically just a fraction of a micrometer in diameter. They are formed from materials released by dying stars, from atoms and molecules that have been blown out into space by stellar winds and supernova explosions. They exist in clouds of remarkable density and extent, clouds that can stretch across light years and contain the mass of millions of suns. And as light travels through these clouds, the dust scatters it, bends it, sometimes absorbs it completely. The effect of this dust on light has been one of the major discoveries in astronomy. When we observe distant stars in certain directions, they appear dimmer and redder than they should be if the dust weren't there. The dust preferentially scatters blue light, which has shorter wavelengths, allowing the redder light with longer wavelengths to pass through more easily. This is called reddening, and it's one of the ways astronomers can detect the presence of dust, even when they cannot see it directly. The dust also obscures our view of distant objects, making them impossible to see in visible light. But if we observe using infrared light, with wavelengths longer than visible light, we can often see through the dust. The infrared light penetrates where visible light cannot. This is why infrared telescopes have been so important in recent decades for mapping the structure of our galaxy. The cosmic dust then contributes to the journey of light across the galaxy. Not by slowing the speed of light itself, which remains constant, but by causing the light to take longer paths, to be scattered and redirected, sometimes to be absorbed and re-emitted in different directions. Imagine light as a traveller trying to cross a landscape filled with obstacles. The fastest path might be a straight line, but if there are barriers in the way, the light must find ways around them. Each detour, each interaction with dust, each scattering event takes time, and across 100,000 light years, across the vast distances of our galaxy, those small delays accumulate. Beyond the dust, there is also the interstellar gas. Our galaxy is not empty space with stars scattered through it. Rather, it is a vast ocean of gas, primarily hydrogen, with traces of heavier elements. This gas is not uniformly distributed. It gathers into clouds of various densities. Some of these clouds are so dense that they collapse under their own gravity to form new stars. Others are more diffuse, filling the spaces between the denser clouds. The gas has temperature, sometimes extremely cold and sometimes heated to thousands of degrees. It has motion, being stirred by the gravity of stars, by supernova explosions, by the rotation of the galaxy itself. And as light travels through this gas, it interacts with it in various ways. When light passes through a cloud of hydrogen gas, it can be absorbed if the photon's energy matches the energy difference between two electron energy levels in the hydrogen atom. This is how scientists can analyze the composition of the interstellar medium. They observe the light from distant stars and look for dark lines in the spectrum, indicating that certain wavelengths of light have been absorbed by gas between us and the star. These absorption lines tell us what elements are present in the interstellar gas and how much of each element there is. But from the perspective of the light's journey, this absorption and re-emission process introduces delays. The light must interact with matter, and those interactions take time, even if the time seems infinitesimal on human scales. The interstellar gas also has magnetic fields associated with it. These magnetic fields permeate our galaxy and can affect how charged particles move through space. While photons of light are not charged, they can interact with magnetic fields indirectly through various quantum effects. Moreover, the magnetic fields are important for understanding the larger structure of the galaxy and the processes that shape it. They help compress gas clouds, aiding in star formation. They carry energy and angular momentum. They create turbulence in the interstellar medium. All of this contributes to the dynamic, complex environment through which light travels. Now, as we consider all of these factors, all of these aspects of the galactic environment that affect light's journey, we begin to see that the answer to our central question, the question of why light takes 100,000 years to cross our galaxy, is not a simple one. It's not just about the distance and the speed of light. It involves understanding the structure of the galaxy, the distribution of dust and gas, the presence of dark matter, the effects of gravity on the path of light, and the various interactions that light undergoes as it traverses this vast structure. It is a question that connects to nearly every field of astronomy and physics, and the work of understanding it has led to discoveries that have changed our understanding of the universe itself. As we continue our journey deeper into this mystery, I want you to remember that you are not simply learning abstract facts about the cosmos. You are learning about your home, about the context in which your species evolved, about the sources of the light that allows you to see the world. You are learning about the processes that created the elements in your body. You're connecting yourself through understanding to the vastness of the universe. This knowledge, this wonder, this sense of connection is part of what makes us human. We are the only species, as far as we know, capable of understanding the universe in this way. We are the cosmos become aware of itself. The journey of light across our galaxy is, in a way, a metaphor for understanding itself. It is a slow process. It requires patience. It requires looking beyond the obvious, beyond what we can see directly. It requires using tools and techniques that stretch the limits of our technology and ingenuity. It requires the dedication and collaboration of thousands of scientists across generations. But the rewards of that journey are immense. We gain understanding, we gain perspective, we gain a deeper sense of our place in the universe. And as the light slowly travels across the galaxy, carrying its ancient messages to us, we are receiving not just photons of light, but messages about the fundamental nature of reality itself. So as you sit in the quiet of the night, perhaps with the stars visible through a window or a clear view of the sky, think about the light that is reaching you. Think about where it came from. Think about the journey it has taken. Think about all the processes, all the dust and gas and gravity that shaped that journey. Think about the fact that by observing that light, by studying it and analyzing it, you are connected to the cosmos in a way that is both profound and real. And as you relax into this contemplation, as you let your mind drift across the cosmic distances, prepare yourself for the deeper exploration to come. We have only just begun to understand why light takes so long to cross our galaxy. The mysteries are deepening, the wonders are multiplying. And you are part of this great adventure of human understanding. Let the vastness of it all settle over you. Feel the comfort of being part of something so incomprehensibly large and beautiful. And in that feeling, find peace, find rest. Find the kind of wonder that stills the mind and opens the heart to the mysteries of the cosmos, because that, ultimately, is what we are seeking when we look up at the stars and ask questions about the universe. We are seeking that sense of connection, that sense of belonging to something greater than ourselves. And tonight, in the quiet and the darkness, that sense is waiting for you, carried on the light of distant stars that has travelled across the galaxy for longer than humans have been on this earth. The puzzle of light's journey continues now as we delve deeper into the central mystery that commands our attention. Consider this simple yet profound observation. Light, this ultimate cosmic messenger, this fastest possible manifestation of energy and information in our universe, somehow takes 100,000 years to traverse the expanse that is our own galactic home. When we sit with this fact, when we truly let it sink into our consciousness, we begin to feel the weight of the mystery. How can something so impossibly fast take such an impossibly long time? What does this tell us about the nature of space, about the structure of our universe, about the very fabric of reality itself? To understand this mystery more deeply, we need to think carefully about what we mean by light taking a long time to cross the galaxy. Light itself, as we understand it from Einstein's theory of relativity, always travels at a constant speed in a vacuum. This speed, 300,000 kilometers per second, is built into the very fabric of space and time. Nothing can travel faster than light. Nothing can reach light speed except light itself. And for light, traveling at its constant speed, the journey across 100,000 light years, by definition, takes 100,000 years. This is not something that slows light down or speeds it up. It is simply a statement about distance and speed and time, the fundamental relationship that defines how we measure intervals in space. But here is where the deeper mystery emerges. When light travels through the universe, through the interstellar medium of our galaxy, it does not travel through a perfect vacuum. We have learned that even the seemingly empty space between stars is not truly empty. It contains gas, dust, radiation, perhaps dark matter. It is filled with the remnants of stellar processes, with the seeds of future stars, with the invisible scaffolding of gravitational fields. In this medium, light's journey becomes more complex. While light's speed in vacuum remains constant, the path it takes can be bent, scattered, interrupted. The time it takes to reach us, the time from the perspective of someone receiving the light, can be affected by many factors. Think about what happens when a photon of light leaves a distant star on one side of our galaxy, heading toward us on the other side. The photon is created in the fusion reactions at the core of that star, where hydrogen fuses into helium, releasing enormous amounts of energy. Some of that energy takes the form of photons, particles of light. These photons scatter randomly in the dense plasma of the star's interior, absorbed and re-emitted countless times before finally reaching the star's surface. When they do reach the surface, they escape into space, and from that moment, they are free to travel in straight lines at their constant speed of light. But before they have traveled very far, they encounter the interstellar medium. Perhaps the first thing they encounter is the stellar wind, the constant stream of particles flowing outward from the star. The photon passes through this wind without significant interaction and continues on its way. But soon it enters a region of denser interstellar gas, a cloud of hydrogen and helium with traces of heavier elements. As the photon passes through this cloud, it may interact with the atoms of gas. A hydrogen atom in a specific quantum state may absorb the photon if the photon's energy exactly matches the energy difference between two electron orbits in that atom. When this happens, the photon ceases to exist for an infinitesimal moment. The energy of the photon lifts an electron to a higher energy level. Then, almost immediately, the electron falls back down to its original level, and the energy is released as a new photon of light. This new photon continues in a direction that may or may not be the original direction of the first photon. This process of absorption and re-emission happens countless times as light travels through the galaxy. Each individual event is instantaneous or nearly so, but they accumulate. They add complexity to the journey. The light does not travel in a straight line from source to observer. Instead, it bounces around, interacts with the medium, takes a somewhat random walk through the galaxy. The path is longer than the direct route. The journey takes longer. Yet this is still not the full story because there is also the dust. As the photon continues its journey, it may encounter a grain of cosmic dust. The dust grain is much larger than an individual atom, made up of billions of atoms bonded together into a solid particle. When a photon encounters the dust grain, it cannot pass through unchanged. Instead, it is scattered. The dust grain absorbs the photon's energy and re-radiates it in a different direction. Dust is particularly effective at scattering blue light, the light with shorter wavelengths, which is why distant stars appear redder than they otherwise would. This scattering process affects how long it takes light to reach us from that distant star. The light may take a longer path, bouncing off many dust grains, being scattered again and again, before finally reaching our telescope and our eyes. Beyond the dust and gas, there is also the effect of gravity itself. Einstein taught us that massive objects warp the space around them. The more massive an object, the more dramatic this warping becomes. In our galaxy, there are massive stars, dense stellar remnants, and most significantly, dark matter distributed throughout the galactic structure. All of this mass warps space and time around it. This means that the path light takes through space is not a straight line. Light follows the curves in space-time created by the presence of gravity. As light travels through these curved regions, its path bends. It takes longer routes. It follows the contours of space warped by the mass it passes near. This effect, called gravitational lensing, when it becomes dramatic enough to noticeably bend light or create multiple images of distant objects, contributes to the complexity of light's journey through the galaxy. So we begin to see that the journey of light across our galaxy is not simple. It is not merely a matter of distance and speed. It is a complex negotiation between the light and the medium through which it travels. The light is constantly interacting with atoms and dust and magnetic fields and gravity. Each interaction delays it, scatters it, bends its path, and yet, crucially, these interactions do not slow light's fundamental speed. Light always travels at the speed of light when in a vacuum, but when we consider the path that light takes, when we consider the total journey from source to observer, we see that the actual distance traveled is greater than the straight-line distance. The apparent delay, the 100,000 years, or whatever the time span might be, is the result of this more complex, less direct route through the medium of the galaxy. This is where the central mystery of our exploration deepens. We have been speaking as if the light takes 100,000 years to cross our galaxy as a simple statement of fact. But we need to ask, is this really what we observe? When we look at light from a distant star, does it take 100,000 years to reach us? How would we even know? How would we measure such a thing? The answer is subtle and beautiful. We do not in fact directly measure how long light takes to travel from distant stars to us. We cannot send a signal to a distant star and receive a reply that tells us the round-trip travel time, the way we might measure distances in our solar system using radar. Instead, we infer the age of the light, the time since it was emitted, based on the distance to the source. And how do we determine the distance to a distant star? We use a variety of techniques, each one more indirect and more dependent on assumptions than the last. The nearest stars we can measure using parallax, the apparent shift in a star's position as Earth moves around the Sun. The farther stars we estimate based on their brightness, assuming that they are similar to nearby stars of the same type. The most distant stars and galaxies we estimate based on the speed at which they appear to be moving away from us, using the Doppler shift of their light. Each technique involves assumptions and uncertainties, and in each case we are not directly measuring how long light takes to travel. We are measuring something else and inferring the distance and therefore the light travel time from that measurement. But this raises a profound question. If we cannot directly measure the time light takes to travel from distant stars to us, how can we be sure that light from the far side of our galaxy actually does take 100,000 years to reach us? Could it be that light somehow travels faster across the galaxy than we think? Could there be unknown processes that accelerate light, that shortcut its journey? Could our assumptions about the nature of light and the structure of the galaxy be fundamentally wrong? These are the kinds of questions that science always asks. These are the kinds of uncertainties that drive scientific inquiry forward. The answer, according to modern astronomy and physics, is that the light travel time from distant regions of our galaxy to us is indeed on the order of the time it would take light to travel the distance at its constant speed. We can be confident in this for several reasons. First, the structure of our galaxy, its size and extent, has been mapped using multiple independent techniques, different methods of estimating stellar distances, while each having uncertainties, generally agree on the overall size and structure of the galaxy. Second, we have no evidence that light travels at anything other than its constant speed in a vacuum. Relativity, one of the most thoroughly tested theories in all of science, predicts this constant speed, and all observations support it. Third, we have observations from sources outside our galaxy, from other galaxies at vast distances, that are consistent with light traveling at constant speed and taking the expected time to reach us from those distances. So while we must always maintain scientific humility, while we must always acknowledge that our understanding might be revised in the light of new evidence, the evidence strongly supports the conclusion that light from the far side of our galaxy does indeed take roughly 100,000 years to reach us. This is not a direct observation, but rather an inference from our best understanding of the universe, and like many scientific conclusions, it is based on multiple lines of evidence and continues to be tested and refined as our observations improve. If you are still with us, still following this journey through the mysteries of light and the galaxy, I want to pause and ask you something. What aspects of this puzzle most capture your imagination? Is it the fact that light interacts with matter in such complex ways, being scattered and absorbed and re-emitted? Is it the realization that we cannot directly measure how long light takes to travel from distant stars, but must instead infer it from other measurements? Is it the subtlety of the question itself, the way that asking how long does it take for light to cross the galaxy requires careful thought about what we mean and what we can actually observe? Please take a moment and think about what fascinates you most. And if you're enjoying this exploration, please like and subscribe because there is so much more to discover together. The mystery of light's journey deepens further when we consider what we have learned from modern instruments and observations. The Hubble Space Telescope, launched into orbit in 1990, has revolutionized our understanding of the galaxy and the universe. It can observe distant stars and galaxies in unprecedented detail, allowing us to measure their properties with greater accuracy than ever before. The infrared telescopes that have been developed in recent decades allow us to see through cosmic dust that blocks visible light, revealing the hidden structures of our galaxy. Ground-based radio telescopes can detect the radiation from interstellar gas, mapping its distribution and motion. X-ray telescopes can detect high-energy radiation from sources that would otherwise be invisible. All of these instruments work together to build a picture of our galaxy and how light travels through it. What has emerged from these observations is a picture far more complex and intricate than earlier astronomers might have imagined. The galaxy is not a static structure, not a frozen snapshot of stars and dust and gas. It is dynamic, it is evolving. Stars are being born in some regions, massive and brilliant, living for only a few million years before exhausting their fuel and exploding as supernovae. Stars in other regions are old and cool, the white dwarfs that are the remnants of stellar deaths. The gas and dust are swirling, being stirred by stellar winds and supernova explosions, falling into the gravity wells around massive objects. The magnetic fields are twisted and tangled by the motion of the gas. The entire structure is rotating, with different parts rotating at different speeds. And through all of this dynamic complexity, light is traveling, being scattered and absorbed and re-emitted, following curved paths through warped space-time. The effect of this complexity on light's journey is profound. Light from a star on the far side of our galaxy does not travel in a straight line to reach us. It may be scattered dozens or hundreds of times. Its path may be bent by gravity. It may be absorbed and re-emitted, changing direction in the process. The actual path that light takes may be significantly longer than the direct distance from source to observer, and all of these factors contribute to the effective delay in the light reaching us. The 100,000 years, then, is not simply a mathematical consequence of distance and speed. It is the result of a complex journey through a complex medium. Yet there is more to the mystery still. There is the question of whether all light from the far side of our galaxy takes the same amount of time to reach us. The answer is almost certainly no. Different photons, starting from the same star, may take different paths through the galaxy. Some may encounter more dust and be scattered more frequently. Some may pass near massive objects and have their paths bent by gravity. Some may take shorter paths and arrive earlier. Some may take longer paths and arrive later. This means that when we observe light from a distant star, we're seeing light that was emitted at different times, following different paths. The light we receive is a mixture of photons that took varying routes through the galaxy. This has implications for how we understand the light we receive from distant sources. When we observe a distant star or galaxy, we're not seeing it as it is right now. We're seeing it as it was in the past because light takes time to travel, but we are seeing it through a lens of sorts, through the medium of the galaxy. That medium has affected the light, scattered it, distorted it, delayed some photons more than others. When we analyze the light to determine the composition of the star, its temperature, its motion, all of these measurements are affected by the journey the light has taken through the galaxy. Scientists must account for these effects, must correct for the dust and the scattering and other processes to get an accurate picture of the source of the light. This is why infrared observations have been so important. Because infrared light, with its longer wavelengths, is less affected by dust scattering than visible light. Infrared observations can sometimes give a clearer picture of the true properties of distant stars. Similarly, X-ray and radio observations can reveal things that are hidden in visible light. By combining observations across the entire electromagnetic spectrum, from radio waves to visible light to gamma rays, astronomers can build a more complete and accurate picture of distant objects and of the galaxy itself. The journey of light through our galaxy, then, is intimately connected to the tools and techniques we use to study the universe. To understand why light takes 100,000 years to cross the galaxy, we must understand what the galaxy is made of, how its structure affects the path of light, how light interacts with matter, and to understand these things, we must observe the light itself, analyze it, measure it, compare observations across different wavelengths and different telescopes. It is a beautiful example of how human ingenuity allows us to overcome the limitations imposed by distance and time, to observe the universe and understand it despite being separated from the objects of our study by vast spans of space and time. As you continue to follow this journey, as we move deeper into the mysteries of the galaxy and of light itself, remember that you are participating in something remarkable. You are engaging with knowledge that took centuries to accumulate, that required the dedication of countless astronomers and physicists and engineers. You are thinking about questions that touch on the deepest aspects of reality, about the nature of space and time and light and matter. You are contemplating your place in a universe that is incomprehensibly vast and ancient and beautiful, and in doing so, you are connecting yourself to the grand human endeavor to understand the cosmos. That connection, that sense of participation in the greatest intellectual adventure of our species, is something worth holding on to as you settle into deeper and deeper states of peaceful contemplation and rest. The cosmic architecture, dust, gas, and hidden forces now unfolds before us as we venture deeper into understanding the fundamental structures that comprise our galaxy. We have established that light takes 100,000 years to cross our galactic home, and we have begun to explore why this might be the case. But now we must examine more closely the actual physical components of the galaxy, the tangible and intangible structures that light must navigate as it journeys through space. We must think carefully about the dust that fills the spaces between stars, the vast clouds of gas that extend across light years, the invisible scaffolding of dark matter that shapes everything, and the warping of space-time itself created by the presence of mass and gravity. When we speak of cosmic dust, we are speaking of something that seems almost insignificant when described in isolation. A single dust grain might be just a few millionths of a meter across, too small to see with the naked eye, barely visible under a microscope. It might be composed of silicate minerals, similar to the sand on Earth's beaches, or it might be made of carbon, or it might have a more complex composition with ices and organic molecules frozen to its surface. A single dust grain would seem to have almost no effect on light passing through it. A single grain would be unlikely to noticeably scatter or absorb a photon. And yet, the galaxy is not filled with isolated dust grains. It is filled with incomprehensibly large numbers of dust grains, gathered into clouds that can stretch across many light years and contain the mass of millions of suns. To grasp the scale of this, consider what we know about dust clouds in our galaxy. There are regions known as dark nebulae or dark clouds, where dust is so densely concentrated that visible light cannot penetrate it at all. These clouds appear as dark patches against the brighter background of more distant stars. The Great Rift, a feature visible from Earth as a dark band splitting the bright core of the Milky Way, is caused by dust clouds blocking our view of stars beyond them. This dust is so effective at blocking light that it has shaped how humanity has perceived the galaxy for all of history. The Milky Way appears not as a complete disk of stars, but as a band interrupted by dark regions, and much of that appearance is due to dust. When astronomers began to understand the true extent of the dust in our galaxy, it revolutionized how we think about the galactic structure. For a long time, astronomers could see stars in certain directions, and had difficulty seeing stars in other directions. Some assumed that there were simply fewer stars in those directions, that the galaxy had a particular shape with dense regions and sparse regions. But as observations improved, particularly with infrared telescopes that can see through the dust, it became clear that the dust itself was responsible for much of the apparent structure. In directions where visible light showed few stars, infrared light revealed countless stars obscured by dust. This meant that our visual perception of the galaxy was fundamentally distorted by the presence of dust. The dust is created by processes in dying stars. When a massive star reaches the end of its life and explodes as a supernova, it releases enormous amounts of energy. This energy blasts the outer layers of the star into space. As these layers of material move outward through space, away from the initial explosion, they cool. As they cool, atoms begin to bond together, forming molecules. Further cooling causes these molecules to condense onto tiny seeds of dust. Over time, these dust grains grow, gaining more material through collisions with other grains, and through accretion of gas. The result is the cosmic dust that fills our galaxy. It is the ashes of dead stars, the material from which new stars will eventually be born. Because dust grains are created in stellar explosions and then gradually accumulate material over time, their composition reflects the composition of the stars that created them. The dust in our galaxy contains silicates, which are compounds of silicon and oxygen, similar to rocks on Earth. It contains carbon in various forms, sometimes in graphite grains and sometimes in more complex organic molecules. It contains ices, frozen volatiles such as water, methane and ammonia, frozen out of the gas phase when temperatures are cold enough. Some dust may even contain organic molecules, complex carbon-based compounds that could play a role in the chemistry of star formation and potentially in the origin of life. When light interacts with dust, the interaction depends on the size of the dust grain compared to the wavelength of light. For visible light, which has wavelengths of about half a micrometer, dust grains that are roughly the same size as or slightly smaller than the wavelength are particularly effective at scattering the light. This is why dust appears reddish when illuminated from behind by starlight. The dust scatters blue light more effectively than red light, so the light that reaches us has had much of its blue components scattered away, leaving it appearing redder. This effect, called interstellar reddening, was one of the first clues that dust was present in the galaxy, even before astronomers fully understood what dust was. The effect of dust on light's journey is significant. As a photon of light travels through a dust cloud, it may interact with a dust grain. The photon's energy causes electrons in the dust grain to oscillate. These oscillating electrons re-radiate the light in all directions, a process called scattering. From the perspective of an observer trying to see the star that emitted the light has been deflected from its original path. Some of the light scatters back toward the star, some scatters to the sides. Only a portion continues forward. The result is that less light reaches the observer, the light appears dimmer and redder, and the light that does reach the observer has travelled a somewhat indirect path. But the dust does more than scatter light. It also absorbs light. When a photon is absorbed by a dust grain, the energy of the photon is taken up by the grain. The grain becomes slightly warmer as a result of absorbing the energy, but eventually the grain will radiate away this energy, typically as infrared radiation, heat. This is why infrared telescopes are so useful for studying regions of the galaxy filled with dust. The dust has absorbed visible light from stars, warmed up slightly, and is re-radiating that energy as infrared light. By observing the infrared radiation, astronomers can detect stars and other objects that are hidden from view in visible light. From the perspective of understanding light's journey across the galaxy, dust is one of the most important factors. Not only does it scatter and absorb light, but it also means that the light path is not a straight line. Light from a distant star may be scattered by dust dozens or even hundreds of times before reaching us. Each scattering event deflects the light slightly. The cumulative effect of all these deflections is to make the actual path that light takes significantly longer than the direct distance from the star to us. This is one of the major reasons that light from the far side of our galaxy takes longer to reach us than a simple calculation of distance divided by light speed might suggest. The distribution of dust in our galaxy is not uniform. There are regions of high dust concentration, such as the dust lanes that appear as dark bands across the galactic disk. There are regions of lower dust concentration, where we can see stars more clearly. The dust tends to be concentrated in the galactic disk, where most of the stars and gas are also concentrated. It is less prevalent in the galactic halo, the region above and below the disk. This non-uniform distribution means that light travelling in different directions across the galaxy will encounter different amounts of dust and may be delayed by different amounts. Light travelling along the galactic plane, where dust concentration is highest, may be delayed more than light travelling more perpendicular to the plane. The gas component of the interstellar medium is far more massive than the dust component. While dust represents perhaps 1% of the interstellar medium by mass, gas represents the other 99%. The gas is primarily hydrogen and helium, the lightest and most abundant elements in the universe, accounting for about 99% of the gas's mass. The heavier elements, carbon, nitrogen, oxygen, silicon, iron, and the rest of the periodic table, make up only about 1% of the gas's mass. Yet despite their small proportion by number, these heavier elements are crucial. They create the dust grains, they play key roles in chemistry and star formation, and they are the elements from which planets and living organisms are built. The interstellar gas exists in different phases, different physical states. Some of it is very hot, ionized into plasma by the radiation from hot stars. Some is warm, at temperatures similar to the temperature of Earth's atmosphere. Some is cold, a few tens of degrees above absolute zero. These different phases coexist in a dynamic equilibrium, with gas being heated by stellar radiation and supernova explosions, and being cooled through radiation of heat and through expansion into lower pressure regions. The boundaries between the different phases are not sharp. Rather, there are gradual transitions, regions where the gas is being heated or cooled as it moves from one phase to another. The cold phase of the interstellar medium is particularly important for star formation. When gas cools enough, it condenses into dense clouds. These molecular clouds, as they are often called because the hydrogen atoms bond together into hydrogen molecules under the cold conditions, are the birthplaces of stars. A molecular cloud might contain millions or billions of times the mass of the Sun, spread across a region that is light years across. Yet despite their large mass, they are still relatively diffuse, with densities that are higher than the general interstellar medium, but still far lower than the density of air on Earth. Within these clouds, gravity causes the gas to clump. The denser regions attract more gas through their gravity, growing larger and denser. Eventually, a region becomes so dense and so hot, due to the gravitational compression, that nuclear fusion ignites, and a new star is born. When light travels through these clouds of gas, it interacts with the gas in various ways. Neutral hydrogen gas can absorb light at a specific wavelength, the 21 centimeter wavelength that corresponds to the transition between different quantum states of the hydrogen atom. This is how astronomers can map the distribution of neutral hydrogen in the galaxy. They observe the 21 centimeter radiation and can determine where the hydrogen is located and how it is moving. Visible light can be absorbed by various other atoms and molecules in the gas, creating absorption features in the spectrum of light from stars behind the gas. These features tell astronomers what elements are present in the gas and how much of each element. The motion of the gas through the galaxy also affects light's journey. The gas is not static. It is stirred by stellar winds, the streams of particles flowing from the surfaces of hot stars. It is disrupted by supernova explosions, which blast surrounding gas outward at high speeds. It is moved by the rotation of the galaxy and by the gravity of massive structures within the galaxy. This motion can cause the light from stars to be Doppler shifted, appearing redder if the star is moving away from us and bluer if it is moving toward us. Astronomers use these Doppler shifts to measure the velocities of stars and gas clouds, to understand the motion and structure of the galaxy. Perhaps the most fascinating aspect of the interstellar gas is its role in the chemistry of the galaxy. In the cold molecular clouds, complex chemistry occurs. Atoms combine to form molecules. These molecules can be quite complex, including carbon monoxide, water, ammonia, formaldehyde, and many others. Some molecules detected in molecular clouds are organic, meaning they contain carbon and hydrogen, the building blocks of life. These molecules are not alive, but they are the kinds of compounds that would be the precursors to life. When a star forms within a molecular cloud and planets form around that star, the composition of the planets is influenced by the composition of the cloud. If the cloud contains organic molecules, some of those molecules may be incorporated into the planets. On Earth, these organic molecules may have played a role in the origin of life. So the molecules in the interstellar gas are, in a sense, our ancestors, the chemical precursors from which we are made. As light travels through the galaxy, it passes through regions with different densities and compositions of gas. In some regions, the gas is so tenuous that light passes through with little interaction. In other regions, the gas is denser and light interacts more frequently. The light may be absorbed and re-emitted, causing delays. The light may be scattered by interactions with charged particles. The light may be affected by the motion of the gas, experiencing Doppler shifts. All of these effects contribute to the complexity of light's journey through the galaxy and help explain why light from the far side of the galaxy takes as long as it does to reach us. If you're still following this journey with us, still engaged in contemplating the structure of the galaxy and the journey of light through it, I encourage you to reflect on what you have learned so far. The galaxy is not the simple structure that early astronomers imagined. It is not just a collection of stars distributed through empty space. It is a complex, dynamic environment filled with dust and gas, with regions of high density and low density, with motion and change everywhere. And light, traveling through this environment, does not travel in a straight line. It is scattered, absorbed, re-emitted, deflected by gravity, affected by motion. The 100,000 years that it takes for light to cross the galaxy begins to seem not so mysterious, but rather a natural consequence of the structure through which the light must travel. Beyond the dust and gas, there is another crucial component of the galaxy that affects light's journey: dark matter. This is perhaps the greatest mystery of modern astronomy. We cannot see dark matter directly. It does not emit light. It does not absorb visible light in any significant way. We cannot observe it with telescopes. And yet, astronomers are confident that dark matter exists and comprises the vast majority of the matter in the galaxy and in the universe. How can we know about something we cannot see? The answer lies in observing the effects of gravity. Massive objects warp space and time around them, and gravity affects the motion of objects around them. By observing how stars move in the galaxy, by measuring their velocities, astronomers can infer the presence of dark matter. The story of the discovery of dark matter is a fascinating chapter in the history of astronomy. In the 1930s, an astronomer named Fritz Zwicky observed clusters of galaxies and noticed that the galaxies were moving too fast. If he calculated the total mass of the galaxies in the cluster based on their brightness, assuming that the brightness of a galaxy is proportional to its mass, then the gravitational attraction between the galaxies should not be strong enough to hold the cluster together. The galaxies should have flown apart, yet the clusters remained intact. This suggested that there was more mass present than could be accounted for by the visible galaxies. Zwicky proposed that this missing mass was dark matter, matter that was present but invisible. Decades later, in the 1970s, another astronomer named Vera Rubin made observations that provided even more compelling evidence for dark matter. She measured the rotation curves of spiral galaxies, plotting the velocities of stars at different distances from the galactic center as a function of distance. The expectation, based on the visible mass of the galaxy, was that the rotation velocities should decrease with distance from the center, just as the orbital velocities of planets in our solar system decrease with distance from the Sun. The outer planets move more slowly than the inner planets because they feel less gravitational attraction from the Sun. By analogy, stars farther from the galactic center should move more slowly than stars closer to the center. But this is not what Rubin observed. Instead, the rotation velocities of stars remained roughly constant with distance from the galactic center, at least out to the edge of the visible disk. This was a puzzle. If the rotation velocities remained constant with distance, then the gravitational force must not be decreasing with distance the way Newton's law of gravitation would predict for the visible mass alone. The only explanation was that there must be more mass present, distributed in a larger halo extending beyond the visible disk of stars. This additional, or invisible mass, would provide the extra gravitational attraction needed to keep the outer stars moving at the observed velocities. The dark matter halo extends far beyond the visible disk of stars. While the visible stars in our galaxy are concentrated in a disk that is perhaps 100,000 light-years across and a few thousand light-years thick, the dark matter halo extends to distances of several times the radius of the visible disk. It is a vast, invisible sphere of matter surrounding the visible galaxy. The total mass of the dark matter halo is estimated to be several times the total mass of all the visible stars and gas in the galaxy. In other words, most of the matter in our galaxy is dark matter, invisible and unknown in composition. What is dark matter? Scientists have proposed various candidates. Some suggest it might be composed of weakly interacting massive particles, theoretically predicted particles that interact with ordinary matter through gravity, but very rarely through any other force. Others suggest it might be primordial black holes, small black holes formed in the early universe. Still others suggest it might be exotic forms of matter not yet discovered. Despite decades of searching, no direct detection of dark matter has been achieved. We know it must exist because of its gravitational effects, but we do not yet know what it is made of. From the perspective of understanding light's journey through the galaxy, dark matter has several important effects. First, the presence of dark matter increases the total mass of the galaxy and strengthens its gravitational field. This affects how light travels through the galaxy. Light passes through regions of warped space-time, regions where the fabric of space and time has been distorted by the presence of mass. According to Einstein's theory of general relativity, mass warps space-time, and light follows the curves of space-time. The more mass present, the greater the warping, and the more light's path is bent by gravity. Second, the dark matter halo extends far beyond the visible disk of stars. This means that light traveling through the outer regions of the galaxy travels through a region of relatively high dark matter density. Even though dark matter does not directly scatter or absorb light the way dust and gas do, its gravitational effects are significant. The cumulative effect of all the mass in the galaxy on light's trajectory contributes to the complexity of light's journey and may introduce slight delays or deflections that are difficult to measure directly. Third, the existence of dark matter raises profound questions about the nature of the galaxy and the universe. If most of the matter in the galaxy is invisible and unknown, then our understanding of the galaxy is necessarily incomplete. We are studying only the visible component, the stars and gas and dust that we can observe. The dark matter remains largely mysterious, yet it is the dominant component by mass of the galactic structure. This means that as we seek to understand the galaxy, we must account for the dark matter, even if we cannot directly observe it. The interaction between light and the warped space-time created by gravity is one of the most elegant aspects of Einstein's relativity. According to general relativity, light does not experience a force pulling it in the direction of gravity. Rather, light follows geodesics, the shortest paths through curved space-time. When space-time is warped by the presence of mass, the geodesics are curved. Light follows these curved paths, and the result is that light bends when it passes near a massive object. This effect, called gravitational lensing, was first observed during a solar eclipse in 1919, when the sun's gravity was observed to bend starlight passing near the sun. The observation of this bending provided experimental confirmation of Einstein's prediction and established general relativity as the correct theory of gravity. In our galaxy, gravitational lensing by stars and other massive objects is probably not a dominant effect for most light traveling across the galaxy. The stars are not massive enough, and the geometry is usually not right for dramatic lensing effects. But the cumulative effect of the galaxy's overall gravitational field, shaped by the distribution of visible mass and dark matter, does affect light's path. Light traveling across the galaxy follows slightly curved paths through the warped space-time. These curves are subtle, but they are real, and they contribute to the overall complexity of light's journey. Beyond the dust, gas, and dark matter, there is one more factor that affects light's journey through the galaxy: the magnetic field. Our galaxy has a magnetic field, a vast pattern of magnetic forces that permeates the galactic disk. This magnetic field is believed to be generated by currents of charged particles in the galaxy, particularly in the hot plasma of the interstellar medium, and possibly in the accretion disk around the central black hole. The magnetic field is not uniform. It has a pattern, with field lines aligned roughly with the spiral structure of the galaxy. The strength of the magnetic field varies from place to place, stronger in some regions and weaker in others. While the magnetic field does not directly interact with photons of light, which are electrically neutral, it does affect the charged particles that make up the ionized interstellar medium. The magnetic field causes charged particles to spiral along the field lines. It affects how stellar winds and supernova explosions propagate through the galaxy. It plays a role in star formation by helping to support giant molecular clouds against gravitational collapse. And it carries energy and angular momentum through the galaxy, influencing the overall structure and evolution of the galaxy. These indirect effects of the magnetic field do influence the environment through which light travels, and in that way contribute to the complexity of light's journey. One of the most remarkable recent discoveries about the galactic magnetic field is that it appears to have a spiral structure aligned with the spiral arms of the galaxy. This was revealed through observations of the polarization of light, and through radio observations of synchrotron radiation from relativistic electrons spiraling in the magnetic field. The magnetic field appears to be wound up by the rotation of the galaxy, creating a spiral pattern that matches the spiral structure of the stars and gas. This magnetic spiral may play an important role in the dynamics of the galaxy, helping to drive the circulation of gas and maintain the spiral arm structure. The interplay between all these components, the dust, the gas, the dark matter, and the magnetic field, creates a complex and dynamic environment through which light travels. The galaxy is not a static, unchanging structure. It is constantly evolving. Stars are being born and dying, gas is being stirred and circulated, dust grains are colliding and growing, supernovae explosions are blasting material outward, magnetic fields are being amplified and twisted. Through all of this activity, light travels, taking paths that are influenced by every aspect of the galactic environment. When we consider the journey of light across the galaxy, we must account for all of these factors. The light does not travel in a simple straight line from source to observer. Instead, it follows a complex, winding path through a complex dynamic medium. It is scattered by dust, absorbed and re-emitted by gas, bent by gravity, affected by the motion of the medium. The path it takes is longer than the direct distance. The journey takes time, 100,000 years or more, and in that long journey the light carries with it information about the source from which it came and about the medium through which it travelled. This is why the study of light from distant stars and galaxies is so rich with information. By analysing the light in detail, by looking at its spectrum and measuring its intensity and polarization, astronomers can learn not only about the source of the light, but also about the medium through which the light has travelled. The dust and gas leave their signatures in the light. The warping of space-time by gravity can magnify or demagnify the light, making distant sources appear brighter or dimmer than they otherwise would. The motion of the medium causes Doppler shifts in the frequency of the light. All of these effects encode information about the galaxy and the light we receive. So when we ask why light takes 100,000 years to cross our galaxy, we're really asking about all of these factors combined. We're asking about the structure of the galaxy, the distribution of dust and gas and dark matter. We're asking about how light interacts with matter. We're asking about the geometry of space and time in the presence of gravity. We're asking about the fundamental nature of the universe. And the answer is that light takes 100,000 years to cross our galaxy because of the complex, vast, magnificent structure of the galaxy itself, a structure that is far richer and more intricate than our ancestors could have imagined. As you continue to contemplate these mysteries, as you let your mind drift across the cosmic distances and imagine the journey of light through the vast structures of our galaxy, allow yourself to feel the sense of wonder that such knowledge inspires. We are surrounded by invisible structures, by dark matter that we cannot see but know must be there, by magnetic fields that guide the motion of stars and gas, by dust and gas that scatter and shape the light of distant stars. And yet, through observation and calculation and creative thinking, we have learned to perceive these invisible structures. We have developed ways to detect what cannot be directly seen. We have constructed a picture of our galaxy that grows more detailed and more accurate with each passing year. This is one of the great achievements of human civilization, the ability to understand the universe despite our limitations, despite the vast distances and our brief lifespans. We can look at light that has travelled for billions of years and extract meaning from it. We can infer the presence of dark matter that we cannot see. We can map the magnetic field by observing the polarization of light. We can measure the motion of stars and infer the history of the galaxy. Through the use of reason and observation and mathematics, we have extended our senses far beyond their natural limits. We have penetrated the darkness and the distance, and we have begun to understand the cosmos. And as this understanding has grown, our perspective on our place in the universe has shifted. We are not at the center of creation, as our ancestors believed. We are inhabitants of a relatively ordinary galaxy, in a relatively ordinary part of the universe. Our sun is not a special star, but one among hundreds of billions in our galaxy alone. Our Earth is a small planet orbiting an ordinary star. Our species has existed for only a few million years, a mere blink of cosmic time. And yet, through our consciousness, through our ability to observe and understand, we have become something remarkable. We are the universe become aware of itself. We are matter and energy arranged in a way that can contemplate its own origins and destiny. We are both infinitesimally small and infinitely important, small in the vast cosmos and yet essential to the cosmos's ability to know itself. Hold this knowledge gently as you relax deeper into the contemplation of the cosmos. Feel yourself as part of this vast structure, part of the galaxy, part of the universe. Feel the connection between yourself and the distant stars, connected through light and gravity and the shared atoms that compose all of matter. Breathe slowly and deeply, and let the sense of peace that comes from cosmic perspective settle over you. The mysteries of the galaxy continue to unfold, and you are discovering them layer by layer, mystery by mystery. The journey continues, and in the continuation itself is the greatest beauty. The mystery of missing dimensions now calls us to consider aspects of our universe that defy our everyday intuition and challenge our ability to perceive directly. We have explored the visible structures of our galaxy, the dust and gas and stars that we can see. We have contemplated the presence of dark matter an invisible substance whose existence is inferred from its gravitational effects. But there is more to the mystery still, because even dark matter, vast and invisible as it may be, might not account for all of the mass in the universe. And beyond the question of matter is the even more perplexing question of dark energy, an even more mysterious force that appears to be accelerating the expansion of the universe itself. As we journey deeper into these mysteries, we move from the realm of the merely invisible into the realm of the profoundly mysterious, into regions where our understanding of reality itself begins to break down. Let us begin with a question that has puzzled physicists for decades. What is the nature of space itself? We tend to think of space as a three-dimensional container through which objects move. Up and down, left and right, forward and backward. These three dimensions are so fundamental to our experience that we take them for granted. Yet physicists have proposed that there might be additional spatial dimensions beyond the three we can directly perceive. These extra dimensions might be curled up so tightly that they are imperceptible at the scales we normally observe. They might exist in such a way that particles and light can only interact with them under special circumstances, such as at extremely high energies. The idea of extra spatial dimensions might sound like science fiction, but it has serious scientific support and appears in several of the leading theories of modern physics. One of the most intriguing possibilities is that the universe has more than 3 spatial dimensions, but the extra dimensions are compactified, meaning they are curled up so tightly that they are undetectable on human scales. Imagine a very thin garden hose. From a distance, it appears to be a one-dimensional line, but if you look very closely, you see that it has another dimension, the circular cross-section. Similarly, our universe might appear to be three-dimensional at the scales we normally observe, but if we could examine it at extremely small scales, we might find additional dimensions. These extra dimensions might be present everywhere, but so curled up that we cannot directly access them. The implications of extra dimensions for light and gravity are profound. If extra dimensions exist, then gravity might leak into these extra dimensions in ways that we do not yet understand. This could explain why gravity is so much weaker than the other fundamental forces. It could explain some of the mysteries of quantum mechanics and particle physics, and it could affect how light propagates through space. Light might not be confined to the 3 spatial dimensions we perceive. It might interact with the extra dimensions in subtle ways. These interactions could introduce delays or deflections in light's path that we are only beginning to understand. But what is the evidence for extra dimensions? The evidence is largely indirect, coming from theoretical considerations and from observations of phenomena that seem to require extra dimensions to explain them. String theory, one of the leading candidates for a unified theory of all forces and particles, requires the existence of extra spatial dimensions. In string theory, the fundamental objects in the universe are not particles, but tiny vibrating strings, and these strings require additional spatial dimensions to allow them to vibrate in the required number of ways. String theory remains highly speculative, and many physicists are skeptical of it. But it has attracted serious research efforts and has influenced how physicists think about the structure of the universe. Beyond extra dimensions, there is the mystery of dark energy. Observations made in the late 1990s of distant supernovae revealed something shocking. The expansion of the universe is not slowing down, as would be expected if gravity were the only force at work. Instead, the expansion is accelerating. Something is pushing the universe apart, overcoming gravity and causing the expansion to speed up. This something was named dark energy, a catch-all term for whatever is causing the acceleration. Dark energy makes up about 68% of the total energy density of the universe, far more than the 5% that is made up of ordinary matter and the 27% that is made up of dark matter. What is dark energy? We do not know. The leading hypothesis is that dark energy is the energy of the vacuum itself, the energy that exists in empty space even when no particles are present. According to quantum mechanics, empty space is not truly empty. Pairs of virtual particles are constantly appearing and disappearing, and the energy associated with these virtual particle-antiparticle pairs contributes to the energy density of the vacuum. The energy of the vacuum might be what we are observing as dark energy. But this raises as many questions as it answers. The calculated energy of the vacuum is vastly larger than the observed dark energy density, a discrepancy known as the cosmological constant problem. This is one of the deepest unsolved problems in theoretical physics. Another possibility is that dark energy is not the energy of the vacuum, but rather a new type of field that permeates all of space, similar to the electromagnetic field or the gravitational field, but with different properties. This field might have negative pressure, causing it to push outward rather than pulling inward like gravity. Such a field is sometimes called quintessence, after Aristotle's fifth essence. If dark energy is indeed such a field, then it would fill all of space and would influence the behavior of light and matter throughout the universe. The implications of dark energy for light's journey through the galaxy are subtle, but potentially significant. If space itself is being stretched by the expansion of the universe, then the distances between objects are increasing. Light traveling across the galaxy is therefore traveling through a space that is being stretched. The stretching is very small on the scales of our galaxy, but it might introduce small effects that contribute to the overall journey time. Moreover, if dark energy permeates all of space, then it is present in the galaxy along with the matter and ordinary fields that we have already discussed. Its presence might affect how light propagates in ways that we are only beginning to understand. The existence of dark energy also raises profound questions about the nature of reality itself. If most of the energy in the universe is in the form of dark energy, which we do not understand, then we are ignorant of the fundamental nature of most of the universe. Our understanding of physics, impressive as it may be in many respects, is fundamentally incomplete. We do not know what dark energy is, where it comes from, or how it relates to the rest of physics. These are some of the greatest mysteries that physicists are confronting in the 21st century. As we contemplate these mysteries of missing dimensions and dark energy, we begin to realize that the journey of light across our galaxy is not a simple story that can be fully understood with our current knowledge. There may be aspects of this journey that involve physics we have not yet discovered. There may be interactions between light and dark matter, or between light and dark energy that we have not yet accounted for. The 100,000 years that light takes to cross our galaxy might be explained partly by the factors we have already discussed, the dust and gas and gravity, but there might also be contributions from physics that remains unknown. This is both humbling and exciting. It is humbling because it reminds us of how much we do not know. Despite all the progress that science has made, despite the tremendous increase in our knowledge over the past few centuries, there remain vast areas of ignorance. We do not understand the nature of dark matter or dark energy. We do not know if extra dimensions exist. We do not fully understand the relationship between quantum mechanics and gravity. We are in many ways still in the early stages of understanding the universe. But this ignorance is also exciting, because it means there is so much more to discover. The great mysteries of the universe await solution. Future generations of physicists and astronomers will work on these mysteries and will, hopefully, achieve breakthroughs that deepen our understanding even further. And as they do, the journey of light across our galaxy will be understood in greater and greater detail. We might discover that we have been missing important factors all along. We might find that the answer to our question involves physics that we have not yet imagined. If you are still accompanying us on this journey, still contemplating these deep mysteries of the cosmos, I want to invite you to think about what it means to have such profound ignorance at the heart of our scientific understanding. We understand gravity and electromagnetism and the forces that hold atoms together. We can calculate the trajectories of planets and predict the behavior of stars. We can build technologies that allow us to observe the universe in exquisite detail. And yet, we do not understand what most of the universe is made of. We do not know what is causing the universe to accelerate in its expansion. We can only speculate about whether extra dimensions exist. What does this tell us about the nature of understanding itself? Perhaps it tells us that understanding is not a destination but a journey. We do not arrive at complete knowledge and then stop. Rather, we are always discovering new layers of mystery, always finding that our knowledge is incomplete. Each answer we find leads to new questions. Each mystery we solve reveals new mysteries. And in this ongoing process of discovery, in this endless journey toward greater understanding, we find meaning and purpose. We find the wonder and awe that comes from contemplating the profound mysteries of existence. As you sit with these thoughts, as you let them settle into your consciousness, allow yourself to feel a sense of peace with mystery. In a universe that contains so many unknowns, in a universe where most of what exists is invisible and mysterious, there is a strange comfort in accepting that we do not have all the answers. There is a freedom in acknowledging that our knowledge is limited and will always be limited. There is a beauty in the pursuit of understanding, even though the pursuit may never reach a final destination. The mystery itself is part of the answer. The questions we ask are as important as the answers we find. The universe is vast and ancient and incomprehensibly complex. Our galaxy is one among hundreds of billions, each containing hundreds of billions of stars. Most of what exists is invisible to us, unknown, mysterious, and yet we are here. We are conscious, we're capable of observing and understanding. We can look at light that has travelled for eons and extract meaning from it. We can infer the presence of invisible dark matter and dark energy. We can ask questions about the nature of space and time and reality itself. We are improbable and remarkable creatures, consciousness arising in a universe that seems indifferent to consciousness. And in that remarkable fact lies perhaps the deepest mystery of all. As you drift deeper into relaxation and contemplation, remember that you are part of this vast cosmic structure. The atoms that make up your body were forged in stars. The calcium in your bones, the iron in your blood, the carbon in your cells, all were created in the nuclear furnaces of dying stars and scattered across the galaxy by supernovae explosions. The light of those distant stars has travelled across the galaxy to help shape the world in which you live. You're made of stardust, quite literally, and you are connected to the cosmos in the most intimate way possible. The mysteries of the galaxy are your mysteries. The journey of light across the galaxy is a journey that touches you directly. Let this knowledge settle deeply into your awareness. Feel the connection to the cosmos. Feel the peace that comes from understanding that you are not separate from the universe, but a part of it. Feel the sense of belonging that comes from knowing that you are made of the same material as the stars, that you are shaped by the same laws that shape galaxies and light itself. In this feeling of connection and belonging, find rest. Find the quiet that comes from releasing the need to understand everything. Find the peace that comes from accepting mystery and wonder as fundamental aspects of existence. The journey continues, and there is still much more to explore and discover. The greatest mysteries still await us. But for now, in this moment, allow yourself to simply be present with what you know, with what you do not know, with the infinite possibilities of a universe that is far larger and stranger, and more beautiful than any of us could have imagined. In the darkness and silence, in the vast emptiness of space, there is light travelling, ancient light carrying ancient messages from distant stars, telling the story of a cosmos that is alive with mystery and meaning. End.